Okay, so I get to do the fun introduction. Dr. Callahan. John he graduated here in 2021, his PhD in climate. Dr. Leathers, and his master's with Tracy. Yay. This is my bio, so I'll give you that, but Dr. John Callahan, let's see. Currently, I'm going backwards. You also have a Bachelor of Science degree in Physics and Mathematics. Wow, you sound really good. I'm expecting high things. So he is an interdisciplinary applied climate scientist at Ocean Associates, Inc., working at NOAA Center for Operational Oceanic Products and Services, where he serves as a subject matter expert on sea level rise and coastal hazards, with a focus on friends, focus on friends and trends, prediction and predictability at climate timescales. His work spans several products and includes a combination of scientific research, operational products, and public and professional engagement. John has also contributed to national efforts at the U.S. National Climate Assessments in 5 and 6, and the U.S. Climate Variability and Predictability Program. Locally, he led the development of sea level rise projections for the state of Delaware and is providing guidance to several state agencies and the Delaware River Basin Commission on coastal risk and climate science. Today, Dr. Callahan is joining us to talk about high tide flooding prediction in the U.S., R2O, and back again.
Thank you, Terry.
Cool. Welcome.
Oh, thank you, Terry. It is interesting to be back in this room where I know a lot of memories in this room. I know Terry mentioned 2021 graduating, but that doesn't quite tell half the story there. And I'll go into that. But it is interesting. I just spent a few minutes walking around looking at the 203 lab and looking at the break room and thinking about this room where I spent a lot of years as a graduate student. Too many years, but we had a good time. So what I want to talk about today, and I know this is our kind of the celebration of the 100 years of geography. Ooh, excuse me. Celebration of our department, 100 years in our department. So I'd like to start really by going through kind of my journey through the department, what the department meant to me and how it helped me in some of the positions that I've had. Then I'll get into the actual talk of the title and abstract or the title that I put in, talking about high tide flooding. It's a priority project, hot topic right now that we're doing at NOAA. So we'll get into that, but I do want to start by.
Sorry to interrupt, sorry, excuse me. They can't see on Zoom to share can you share your screen?
I probably can.
Sorry, I don't mean it, but they.
No, go ahead, good idea.
That on Zoom, where's the Zoom? Here we go.
Oh, you're right. It is.
Yeah, that's okay. Where's your screen? Oh, wait, where is it? That's the one? PowerPoint slide, there we go, okay. Okay, there you go, sorry.
I did it on my end. You're recording. Sorry. Okay.
Good. One of these days we'll get technology right. But that's fine, maybe it's a blessing where we do always need, right? The in-person interaction. And that's something for myself working the past few years remotely at NOAA, and I'll mention this a little bit later, but which is nice, but you do need that in-person interaction. And it's so much is about interaction more it is than about the topic and the work you do. It really is. I'll hit more of that later. But I do want to talk about this kind of unexpected journey here. Technology again, wait a minute.
No, we just have to hit your screen once because it's in the Zoom mode.
Yeah.
There you go.
There you go. Okay, thank you. As Terry mentioned, undergraduate degrees in physics and mathematics. Now, I came to UD in 1995, right, which is a lot different than what, graduating in 2021. You're talking about two different worlds there, really. But came to 1995, and my undergraduate degree at Temple was in physics, mathematics. I had 2 degrees. And I had summer internships, right? I had one summer internship at the Naval Air Development Center, NADC. It was great. Polymers and composites, material science, right? That's what I did for 2 summers. And it's hard to see here. This is a large autoclave system. This is exactly what we did, laying up carbon fibers in different orientations and then curing them for 8 hours and taking them out, cutting them up and running all the mechanical tests and talking to the engineers and saying, okay, instead of having 24 layers, let's have 36 layers and put these at 45-degree angles at every one and a bunch of things. Or maybe we've got to heat it for an hour more at a certain atmospheric pressure, et cetera. Then I spent 2 summers in nuclear physics. I started moving away from material science and wanted to get more theoretical. Spent 1 summer in a low energy nuclear physics lab and 1 in a high energy nuclear physics lab. And it's also hard to point out that this is our actual, we called it the Big Mac. It's where we actually had nucleus collisions, you know, sending chlorine atoms into molybdenum, neodymium, and some of the other larger atoms, and then looking at the scattering that took place in there. Really kind of cool stuff. Low energy because it was low, you know, MeVs and when you're sending it in, versus the high energy, which is more proton-proton collision. Okay, this is great. I came to UD, I was gonna do physics, I was thinking nuclear physics, this is the way to go, right? Maybe contribute to the energy, you know, problems that we have in the world. But you know, while in physics one summer, and I was a TA there for my first summer in physics. And one summer, that first summer, I wanted to have a job for the summer, right? I was doing a TA, but I just wanted to do more work, wanted to make more money, et cetera. And somebody said, go to geography. They have, you know, positions in the summertime. They hire students, right? I'm like, geography, right? I'm doing all math and physics, undergraduate. I'm like, geography. What am I going to do in geography? Came here, Janice Fry, who was in the main office, said, oh, yeah, Tracy's down in the office. You could talk to Tracy. So I went down there and she talked about Amazon rainforests, changes in the hydrologic cycle, you know, based on burning and looking at, you know, different time periods before peak burning and after burning. And we use satellite remote sensing to observe this, and we could look at the land surface and the atmosphere. And I just thought, oh, this is incredible. What an awesome application. And it felt good, right? That's the most important thing. It felt good. So I was like, yes, I transferred whole departments. 3 weeks later, I'm in the geography department, right? Right. That's not something I'd advise the students to do, really. Okay. I mean, I'd advise you to go where your passion is and what you love and what speaks to you. But just totally changing your whole, in graduate school to another department, yeah, I'm not sure. My first semester, I was supposed to be an RA for Tracy. I don't know what it was, a month or a few weeks before. It's like, oh, well, we need a TA. And John, you were a TA for physics. I kind of like won the TA award for physics. So it's like, oh, he can teach. Let's bring him in. Can you teach half-time GIS, half-time Fortran? I'm like, sure. What does GIS stand for? And I've never written a Fortran program in my life. So, sure. I had taken a Fortran course as an undergraduate, but this was like really before computers. So the programs I had to write, I took out a pencil and paper and I wrote down what the program would look like and handed it in, right? That was my code. And no program was longer than 2 pages. That was it. So I had to TA those. So I'm like, okay, I'm TAing courses. I have no idea what they're about. Right, I'm in a new program. My entire undergraduate degree and my 4 years in high school, I did not take any geography, any environmental science, any meteorology, any climate, anything. I was math, physics, engineering. That's what I was. So I'm in a whole new program. No idea about any of these courses and TAing courses I have nothing about. But I'm like, okay, like what did I really do? Right? I'm not gonna, you know, I told my mom and she's like, are you sure you know what you're doing? I'm like, yeah, don't worry about it. Don't worry about it. It's fine. I like what I'm doing. And really, I wasn't, at that time, maybe I could have been clueless or maybe I was naive, but I was really enjoying the work. You know, I love, in this room, this was our computer lab. And I spent a lot of time sitting on that windowsill right in that corner, a lot of time on all the computers in this corner. We just came into the computer lab all the time. Good or bad, but we had a great room in the computer lab, and that's where a lot of graduate students where we met. I really love my time here. RA, TA, I did thesis work. I had a whole project on solar radiation modeling that I kind of wrote Fortran code for. Really, I was like a kid in the candy store, writing all this code. This was fun. I did summer work for DGS, writing basic program code to hit stream gauges out and bring them back and create hydrographs in real time. I thought this was cool, real monitoring, connecting the data, looking at it. I worked for a Center for Drug and Alcohol Studies. I taught them GIS. I wrote an RQ 3.2 document of remember, it's 32 pages. Here you go. And I mapped out all of the drug and alcohol, behavior and patterns for K through 12 throughout the state of Delaware. I had a fellowship at RDMS, Research Data Management Services, doing a lot of GIS and web development, a lot of US Census data, metadata clearinghouses. Now, if you look at all this, and again, it's like a kid in a candy store. I was all theoretical in math and physics, and now I'm real world applications of all of this stuff. There's not a whole lot of thesis work, right? So again, not something I recommend to people. During my time as a graduate student, where the thesis work was it was always there, but I spent so much time with this. And I'll apologize right now to Tracy. Sorry, I was all over the place looking at this stuff. And I unfortunately left UD without finishing my master's degree. Not, again, something I would not recommend. I jumped right first into EarthSat, doing satellite, Landsat, remote sensing in DC, right? That was really fun projects, federally funded. We had several 24, 27-hour sessions of 10 people all looking at satellite imagery all the world, making sure they overlap and match. Really kind of cool stuff. Worked for Esri a little while, for a year, doing online mapping and all things GIS. If you work for Esri and you walk into a GIS workshop or a conference, you're gonna have 10 people come up to you and say, hey, how do you do this? How do you do that? I was into spatial analysis and geography, and I was a climate and weather person, really. And they're asking me about databases, or how do I make my labels, 1 point larger on this map? And how do I do digitizing, spaghetti digitizing on a digitizer? And then I came back to UD and worked for RDMS. I did a lot of that same kind of stuff I did before as a student. One particular thing I did was the Delaware Data Mill project, where we worked for the state and federal groups. And here's a picture of several of us. Tina Callahan, my wife, was also one of that project. We went down to DC and we got an award for this work, this Delaware Data Mill. We actually were invited to Esri, the large scale conference, and presented this work, Tina and myself, to 12,000 people, stuff that we're doing in Delaware. So again, getting into it, I love this stuff, right? There's a lot of work there. I did GIS for all departments, from business to political science to nursing, you name it. But I never quite felt at home at these jobs. I always felt like I was the scientist in an IT world, or I was a meteorologist doing something else. So I changed jobs to Geological Survey, which was a more science-based organization than all this GIS and IT stuff. But of course, a big part of my job was doing GIS and data mill. That's what the job was. But at least a part of my job was going to be getting back into science. So what did I do? I spent most of my time doing websites, content management systems, online mapping, things like that. It was fun. It was applications of real science. I started to get into the geology of Delaware too. But it always didn't quite feel like this is it for me. And after about 5 years of not quite really, finding it, I'm not making progress where I wanted to. It's like, I got to reach back out to geography. I reached back out to Tracy and said, that master's thing I started years ago and I never really quite finished, let's get back to it. And fortunately, she did. Tracy did welcome me back. We sat down. She kind of guided me and helped me kind of refocus my efforts on that, and graduated in 2014, which was great. Finally finished that. If you remember the date I started before, 1995, and then finishing in 2014. So it looks like it's a 20-year master's, but not necessarily. No. Then I thought, you know what? I'm back into it, right? Okay, I'm back into geography. I'm talking to the department, going to seminars. I'm gonna get back into my PhD. So I talked with Dan. Dan was like, yes, I'll work with you in a PhD. I'm like, let's do coastal flooding. I was doing some of that work with SEMA and DIOS. It's a big part of my EGS work. Great, I'm like, that's gonna work, right? I have a job, I'm doing coastal flooding. I'll do a PhD in that same topic, right? It's not gonna take 20 years this time. It's gonna be a lot shorter, right? So what happened? Right after that, the state comes to DGS and said, we need to have this huge, massive work on coming up with climate projections and sea level projections for the state of Delaware. hey, John, you're the climatologist in a geological survey. This would be a job for you. So I'm like, oh, okay, that's great. Sure, why not? And I really got into it and loved it. That's the cover of the report over there on the right. That report won an award thanks to Dave Lunch. It was an applied geology award. Got a lot of press, great. But I'm like, okay, that took like 2 years to do, right? And I coordinated scientists, other departments, other state agencies, worked together, great experience. But I didn't let it deter me after that, not like the masters. In this case, as soon as that project was started, I jumped right back into the PhD and was able to finish in 2021. So again, 2021, right, 20 something years, 25, 26 years after I started in UD, finally got that PhD. Okay. So I came back to the department. Fortunately, they welcomed me. I was able to do that kind of work. Then I had a new role. I was a visiting assistant professor for a short period of time. Taught courses in climate change, physical met, climate, GIS, a few other things. Loved my time here, working with the students, continued to have research projects with team, and was also doing that national work that Terry mentioned before, about the National Climate Assessment. And because of that work, the National Climate Assessment and state leadership, I was a good fit for this position I'm currently in at NOAA. A very unique role. I was a subject matter expert in sea level rise. That's what they brought me in for, 100% applied science, which was great. They do a lot of GIS, web development, websites and all that. I don't do it. I can actually ask somebody else, hey, can you add these tables to a database? Hey, can you do this over here? Can we make that change? And not only that, they come to me, which is great. They're doing a report. They're putting up a new website. Hey, this is what we want to do. John, can you review it? John, what do you think about it? Because I'm the climate person there. And it felt good that my unique role and contributions actually meant something. It's not that I was a fish out of water, or I had this imposter syndrome that I shouldn't be in all those previous places. I mean, I did have that, but I started to realize that my contributions were important. My contributions were important and they were valuable. Having that other perspective and the things that I learned in my training, in the department or my different experience helped the other groups. Being a scientist or a meteorology person in a geological survey, or being a scientist in an IT group, being a climatologist, a bunch of oceanographers. So it's really interesting. Maybe you don't quite feel at home, but there is an important role. And your training, you could apply to that. I made a list of different projects that I've worked on during the time. Lots of things from, dendrochronology and tree ring growth to LIDAR and classifications of marine. Classifications of satellite imagery, marine spatial planning, you name it, right? So I made a whole list. And then I was like, okay, I need page 2, right? And I made a whole list of all these different projects, like a lot of cool stuff. Again, good and bad. Not sure I'd recommend all that. But the one thing that was really cool is the things I learned in this department, right? Geography itself is very broad, as you all know. You have the geographic perspective that you start with, no matter what part you're looking at, human dimensions, physical dimensions, process, interactions, relationships. And there's also that physical human interdependent relationship. And I couldn't find a good word. That's on me. I know there are better words to describe this. But the physical processes that happen, especially with climate change and long past trends and the seasonality, right? They affect humans, they affect, right, the biology, the ecosystems, that affects the human systems again, and affects the physical systems, et cetera. A constant interdependent relationship. So these kinds of skills, that perspective, not just skills. Skills is more training and knowing the equations and knowing the programs, et cetera. But having this perspective and knowledge really is important to many different projects, whether it's federal funded at the level or it's down to, one street. Kevin and I have done projects where you're looking at one street in Bowers Beach or Woodland Beach, and that's all they're concerned about at that time, because that's what that project entails. But you can still bring that kind of perspective in that relationship. The numbers you're doing, back in my physics days, they were all numbers, and it's like, it's equations that govern the numbers. But now, since I started with geography, how many years ago, Those numbers are not really numbers. Those numbers of impact people. Those numbers might be of people. They might be of animals. They might be of lifespans, et cetera. So it's important perspective that I have that I bring to, now that I've understood, that I can bring to different projects that I'm part of. So I do value the training I've had here. Not that I expected any of this and where I ended up and where I went, but that perspective and the skills that I've learned throughout really helped and applied to all of those projects that I've mentioned. So that's kind of my background. I'll say this unexpected journey. I've enjoyed it and it's ongoing, right? This is just a moment in time of what's happened before and we'll see what things happen in the future. Yeah, government shut down and all. Right, I work for NOAA, government is shut down. Let's keep those separate for today. But I do want to transition into a project that we're doing at NOAA called high tide flooding. And that was 20 minutes. That was not bad. Okay. High tide flooding, outlook, researched operations, and backing. You know, another reference similar to the unexpected journey. But you'll see that these things kind of build. A lot of what I just mentioned about having that certain perspective and that mission and that drive, that's important, even for projects. And that's the one thing I want to mention here that we'll get to. I mentioned other people here, myself, Matt Collin, John Ratcliffe, right, Greg Bissett, Karen Kavanaugh, Anna Keeney, Ocean Service people, co-ops, great people to work for. And I will definitely say that, and I mentioned this, I think, to Kyle in the hallway, it's extremely impressive, the group of people that I work for in NOAA, particularly at co-ops. You have a lot of dedicated people, and I was very impressed from day one. Camaraderie, respecting each other, and bringing everybody into all of our meetings. It was very easy to work remotely with this group. They went out of their way to bring them in, so I really owe a debt of gratitude from them. And actually, Greg is going to be on campus next week. He's the seminar speaker for the Center for Coastal Research. So he'll be on campus actually talking about a few of the projects that we work on together. That'll be next week. Hey, I mentioned co-ops. Co-ops, if you're not familiar with co-ops, if you look at it from kind of a climate meteorological standpoint, you have those co-op stations. Co-ops in the Ocean Service, we do the data. All those tide gauges that are out there, the buoys, the water temperature, that's us. If the bridge goes down, like what happened in Baltimore, it was in that collision, that was our group that went out there, put temporary buoys out there, measured the currents, looked at the bathymetry, the contours for safe navigation, right? That's what we do. Fortunately, which is kind of cool, just like the Weather Service does for the weather and meteorology, we do that for the ocean and the coastal areas. So in the federal budgets, almost all the budgets that I've seen, the draft budgets, co-op, they've been very kind to co-ops. We do the data, we do the work, we provide that information out to people. So fortunately, hopefully, things will stay, our missions will stay similar, our expertise, our equipment we have, or staff expertise, hopefully will stay around. But we do a lot more than I anticipate. Okay, high tide flooding. So we're talking about water levels along the coast and flooding. And this is not like rainfall, where you have heavy rainfall in those low areas that just kind of have water that can't drain out, or you have a lot of runoff that pools. This is what's going on from the coast, from the oceans coming in, right? You might have your average water level. Where is water level to begin with? You kind of have sea level rise, gradually moving it up. But then you have all these other things, right? You have the storm surge from winds. You might have river downflow. You might have ocean currents. The water expands, actually thermal expansion on the coast during warmer times, et cetera. On the far right, you also have land sinking. And here in Delaware, that has been happening gradually, only a millimeter or so or two a year. But you add it up over hundreds or thousands of years, right? It makes a big difference. So there's lots of going on and all these different pieces, right? You have full research projects. Each piece is like its own discipline, and how do you study and model it and understand it? Well, you can break those down into different time periods. Winds and waves, and let's not worry about tsunamis at the moment. And you have storm surge, right? These things happen on minutes to hour time frames. So you have certain kinds of models and understanding of what's going on there. You have the climate, right? The large scale, like I mentioned, maybe the vertical land motion on bottom, but you have these large scale climate indices that might change the wind patterns or the atmospheric pressure patterns that just make the prevalent winds, you know, a little bit different than what they are usually, or the ocean currents a little bit different. Seasonality is a big. But the tides is something, and again, with my PhD work and maybe the late 2000s or the sea level rise work, I really started to realize there is a huge advantage here, right? We can take advantage of the predictability of the tides. Looking at the average conditions over a time period, we could see the oscillations and wave patterns. We know the physical forcing of the sun and the moon, and of the geography and bathymetry and geomorphology. They all play important roles in tides. But we could take advantage of that. And if you look throughout the country, the areas in blue is tide dominated, and the areas in orange and red are the ones where a lot of our flooding is not tide dominated. These are more storm-based or storm surge, or not necessarily waves, but mainly storm surge. So even though we do have a lot of tides here, our tides are not what flood us. Right? We're starting to get into a new regime, but generally it's not. We have storms where we are. Happens a lot in the Gulf Coast as well. But still, the different physical processes, and I had to put on this map, right? It's a geography talk, and I think about it this way. Some areas are big storm surge based, right? We might have storms for extratropical and tropical systems. The Gulf Coast, almost all their flooding comes from tropical systems, almost all of it. Tides are not happening. Over in the West Coast, even like San Diego and Southern California, El Nino is the big thing that causes flooding because you have these currents coming up, equatorial Kelvin waves. They're coastal track Kelvin waves coming up. They're very warm waters. So the elevations, height of the water is already larger because it expands because it's warmer. You also have different weather patterns up here on the coast. There's not a shelf on the West Coast. So waves are the big thing they have to worry about, especially in the Hawaiian Islands. We have a very narrow shelf. We have a narrow shelf, but it's still thick enough that water can build up. So waves are not necessarily the issue here, but storm surge in the East Coast. So different physical processes, different kinds of models, depending on where you are in the country. Are they tide-based or are they not? Is it waves or is it surge? It gets complicated. But when we're talking about high tide flooding, most of the time we're talking about, and flooding in general from the coast, is it flooding or not? Right, that's the question. Yes or no. You know, you could imagine a bathtub. Now, I don't want to go right to bathtub models, but if you think about a bathtub, you can be having the water running in a bathtub. It's not overflowing. It's not going over its sides. The water is getting higher, but it's not going over. But as soon as it reaches that top, now it's flooding. There's a yes or no thing. There's a threshold. As soon as that water hits, now you start seeing impacts. Generally, NWS started this. They kind of had three different classifications. You know, minor, moderate, and major, right? This is something they had 15 years ago. But it tells the story. Minor is about 1 or 2 feet kind of above your average high tide in general. That's when they start sending out advisories. Disruptiveness, right? It's disruptive of communities. You have to change when you drive. You have flooding in the streets. Moderate and major is when you start to get damaging and destructive kind of flooding. More widespread flooding, not just in local vulnerable areas or low-lying areas like with minor. You start getting the bigger ones. Now, most of the time, we just use the minor as kind of this threshold. Let's just talk about this minor threshold, because that's where flooding stops. That's where we start to see, again, disruptions to the transportation system, disruptions to personal property. You start to get flooding in maybe coastal forests and wetlands. Things start to happen. So we talk about this minor threshold. Here's an example for Charleston, South Carolina, and I kind of highlighted this in one of those maps. This is looking at water level data in the 40s and 50s. And if you think about the first 50 years or so, you might only have 10 floods that cross that threshold. But the gradual increase in water levels, and I think most of us are used to this now, right? We see this trend. This is what we call a general trend. In this case, it's almost linear. Water levels are increasing slightly, but that makes the number of high tide flooding events crossing that threshold rise almost exponentially. From 10 floods in 50 years to 10 floods in 5 years. It's a huge difference, just in a gradual sea level rise. If we look at just the last 5 years, for those 10 floods, They're not regular base. Right, they come in bunches. Mainly because of the tides. We just experienced king tides down in Florida and other parts of the country. These king tide, one of the tide gauges in Virginia Key in Florida, they just set a record of crossing their moderate threshold, I think for 9 days in a row. I mean, that's incredible. You have to start changing your language if we start getting these flooding this frequently. And if you look at a simple sea level rise projection, the same location, small changes vertically, where sea level rise is now 45 days a year. This starts to change where you put your money. If you're a state or local government, how do you protect against this? All of a sudden, now you have to put in money to protect against sea level rise versus maybe new streets or fixing potholes or supporting tax assessments like we see around here. Looking at Delaware, this is actual data from Lewis. The same kind of thing. We have the minor, moderate, and major thresholds listed on the right. This is the maximum water level we hit each day for the past 80 years or so, 100 years. And we look at the number of flood days per year in that bottom chart. We go from, in the 50s and 60s, 5, 10 times at most in a year for decades. And then all of a sudden now we're at the 30, 40, 50 days a year. This is why a lot of our reports that we do at the federal level and internationally, we are entering a new flood regime, right? That threshold, the Weather Service and the Ocean Service, we have our own thresholds. Don't get me started why we have our own thresholds, but we have our own thresholds. But those were decided and chosen because that's where disruptive and impacts apply to people, the streets, right? Public safety, right? Where people live, how ambulances and fire engines can get to places, right? You have the flooding of areas and it mixes with heavy metals or might mix with bacteria or it's huge impacts from just a few days a year to 10, 30, 50 days a year, right? This is a new flood regime. And if you take Lewis data and you look at sea level projections that we have, it's kind of a scary graph. Here are those same observations. We are in this period of rapid transition that even the lowest sea level rise scenario, just based on a linear trend from the past few decades, is going to cause a continued exponential increase in flood frequency rates. How are we going to deal with it? By we, I mean kind of the state, I mean the federal government, I mean lots of people. How are citizens going to deal with it? How are they going to protect? Do they want some money going towards building dunes and berms and construction projects? How do we do those? Is it hardscaping? Is it living shorelines? These are all questions we're going to be dealing with in the future with sea level rise. And even if we stopped, putting, fossil fuels and greenhouse gases in the atmosphere and the temperature is stabilized within 3 years or 5 years, sea level rise will continue. There's an inertial heat content. There's a commitment. Like I said, if all that heating stopped, sea levels will still continue for 100 years, if not more. Hundreds of years. This is something we need to deal with. Now, high tide flooding itself. Short-term timescales, weather timescales, we have lots of models, atmospheric models, precipitation, storm surge models, they're great. We have a lot of long-term models. Those are kind of based on what-if scenarios. What if the future world looks like this? Well, here's what temperature, precip, and sea level will be. What if the world is like this in the future? What about in the middle, right? We developed, my NOAA group, co-op, coastal flooding and information and climate timescales. Coastal flooding and inundation at climate timescales. And when I was hired, this was the first thing they gave me. Read this report, right? This is kind of your focus. We're going to be building on this. And a big part of this is not necessarily the long term, and that's a big thing, long-term trends, long-term future projection. But a major component of this, and some of that money that went to some BIL funding, it went to the NOAA Ocean Labs, GFDL, Physical Science Lab, a few other groups, to focus on the subseasonal and seasonal aspect of it. This is a big deal. At the same time, NOAA developed this service delivery framework, where the idea is that instead of us building products, we do research, okay, we build some products, okay, and we kind of do it in vacuums. I mean, a lot of us do it, a lot of groups do it, federal groups did it as well. You had the data people and the The people that are out in the field and the technicians, you're observing data, you got your database and IT people processing that, and you got some people developing products. But it wasn't necessarily integrally tied to the public and the people that are receiving that information. So this is kind of a new paradigm. And this was maybe 5, 6 years ago, so it's not like last year. So it's something that's been in the mind for quite a while. We had an old high tide bulletin that came out. Well, we're replacing it. We replaced it with this new product that I'll mention in a couple of slides. So that's kind of our delivery aspect, an example of this delivery framework. But you can then assess that on how well it's actually helping people. How well are they seeing it? What kinds of communities are there? What are they seeing? Are they even understanding the data? But we need to gather that data. So we have to have workshops and engagement and reach out and talk with them. In co-ops, about 5 years ago, they created a new stakeholder services branch, SSB. It was never in existence before, but they created it just to serve this kind of thinking. We have to spend time and invest in people and effort to reach out and find out, are our products working? And if they're not, why? Why not? Or what things do we need to do? For high tide flooding, what are the stakeholders? Right? Huge number of lists, and it's going to even double and triple this list. So I don't envy the stakeholder and services branch and what they have to do and coordinate these people. And then they have to work with people like myself and the scientists that we're looking at the data and the statistics and the models. And how can all this work together? And then even when we have ideas, you got to talk with the IT people. And can we even get a product out? Then you got to talk with leadership and administration like, yeah, but we got this other important priority over here, or we don't have money for this one over here. It's a tough job. I'd rather deal with, equations and modeling and stuff like that than reach out to people and bring them all in and talk with them. Now, I do that. I know how hard it is. It's not my primary job. I could always go back and say, yeah, I'm the scientist. I don't have to create a report on user needs. So for this high tide flooding, because of this was a need, there was a paper that came out in late 22 on a statistical approach to predict the high tide flooding at the subseasonal timescales. The idea was you break the water levels down, and it was led by Greg Giuseppe. Water levels down to like the tides. Let's really take advantage of that tides and what we understand about the sea level trends. Okay, you add those together, we know there's a threshold in different communities. What's that difference between that threshold? Between the trends and the tides to that threshold where flooding will start? Well, you could develop these non-tidal residuals, the water levels, after you take out kind of your trends and tides, and develop probability distributions, and use that probability distribution with kind of a persistence, right? Like if you're already, 6 inches higher than average last month, then this month you might be 4 inches higher than average, right? There's a certain memory in the system. So you bring all this together, and based on the probability distributions, you can come up with a likelihood that it might flood. Hey, sounds great. And that's the idea. You have the tides and you have sea level. Where is it going to get to that threshold? Usually at high tide, right? I've had many discussions and even some arguments like, why are we calling it high tide? Flooding happens at all parts of the tide, but it usually happens at high tide. And it's not because of the high tide, it's at high tide. Okay, so an example of using the model, right? The top part, the water, the blue is the actual water levels. The orange is actually the tide prediction part. The difference between these two is mostly weather and current, but usually weather. Down here is using the model. And through trial and error, they picked a 5% likelihood of flooding that we can start telling people, hey, it's likely to flood. Now, it caught many of the events, the red dots are actual events, days where flooding was higher than the threshold, but some it didn't. You can see some red dots on bottom that weather system came in that was not part of maybe outside of its typical monthly environment, right? This system is purely data driven. It's not looking at any projections except what was last month's anomaly. That's all we're using and projecting that forward. That's it. No climate models, no anything else. So we thought it did a pretty good job. At 61 of the 92 gauges throughout the world, throughout the country, we thought it was better than the climatology, right? We look at I think we looked at the difference between the standard error of prediction versus the likelihood and did some ratios. Figured out 61 is skillful. over on average, about 35% of the days, not a whole lot of days that it actually captured. But it's better than not having any product at all. This is just the climatology only. And if you add the persistence, kind of did a much better job in the West Coast, in the Southwest, the Pacific Islands. All right, tides are very important there. That heat and inertia is very valuable. It's easier to predict sea levels at the West Coast and Pacific Islands than it is on the East Coast. We're so weather driven. Okay, works great. We thought it worked great, good enough to put out there, right? We didn't have anything else. So we have this research, right? And we looked at it, we assessed the skill, we have metrics, and okay, let's put it out there. We did. How would you think we do that? Any ideas from anybody? How would we take that research and actually put it out there again? Anybody want to guess anything? It's not easy. No?
Website.
Yeah, website. Okay, website, right. That's actually one of the first thing you think about, need a name.
Mhm.
I'm gonna put it out there. I'm gonna send it to people. Media is gonna get on it. Emergency management agencies, right? Need a name. So we call it monthly instead of seasonal or sub-seasonal. People might be confused. And then they would be, because they might compare with other products, right? Sub-seasonal will just throw people off. If you put a product out there sub-seasonal, half the people won't even look at it. What does that mean? That must be from somebody else. Location-based. Has to be location-based. Users, when they go to open this, and it could be a state, it could be a community, it could be the public. I'm going to my house. I'm going to my area of interest. Time-based. I need to know what it is tomorrow, or next week, or next year, or next month. Right now, our focus is not tomorrow, right? There's already a whole host of information from the Weather Service and models for tomorrow. So our focus is on like 2 weeks and out. We go out to a year, even though I wouldn't use it for like, is it gonna flood in April 30th? Has to be understandable. I kind of mentioned this a few times. If it's not, the science is really worthless, and all the research we put into it, if you give it to people and they don't know what it says, and maybe you're confusing in the way you're saying it. It has to be easy to use. If people might understand it, but they're clicking around, or they're trying to get the information through a report, or just a complicated way to access the data. Maybe the only thing they have are phones. So maybe it's not accessible through a phone. Well, guess what? You just lost half your audience. Has to be easy to use. Team expertise. Okay, we got this research, Greg and some of his partners, some of us, let's say, put together this research, we published it, peer reviewed, great. And we put out the product and we run it on a regular basis. Who's gonna run it? Can we support it? Can we improve it? Can we answer questions about it? What kind of expertise do you have in your team to do that? The IT infrastructure. We might have a great idea. We can design a web page and say, this would be great. And the IT guys are like, no, we can't do that. We're not allowed to have that software package on this system. Oh, you're gonna need too many database tables to make this run efficiently. Oh, you need an API that does that. We're like 6 months behind on API development. Right? Code base, this was fun. This research package was developed in MATLAB. I mean, like our research is MATLAB, fine. MATLAB is huge for doing oceanographic research, great. You're gonna give a MATLAB code, and MATLAB needs a license, to run in kind of an operational website environment where people don't even know what MATLAB is. I mean, they know what it is, but they don't code it. So we made a decision in co-ops, everything goes Python. Because we could develop our expertise in Python, you can train people in Python. If somebody is sick or out, somebody else can take over on Python, right? No, you can do it in collaboratories, online, you can do it in background environments. But this was developed in MATLAB. So you have all these things to deal with. Just because you have research doesn't mean you get it in operations. So this is what the product looks like. It's web-based. You have all the tide gauges there. Each model is based on a tide gauge and all of that data for its history. And you click on a tide gauge, and it gives you a calendar, and you can pass through on what is the likelihood of flooding to happen. Again, it's not weather-based, right? This is likelihood based on astronomical tides, last month's persistence, and sea level trends. And we develop these probabilities and coming up with this 5% probability threshold. So this is what it looks like. We had lots of meetings on what it should, on color schemes, and you name it, like, constantly. Working with the IT developers back and forth. You put it on dev, you put it on user testing, et cetera, et cetera. It's out there. Okay, well, what about the next steps then? We talk with stakeholders, they're like, this is great, but I need to know in between those two tide gauges. Can you tell me if it's gonna flood there? Well, we know flooding is hyperlocal, right? It could be just, a mile away, all of a sudden, it's not gonna flood because you're you're in the back bay, or geomorphology is different. Communities use different thresholds. We might have a threshold set at a tide gauge by the Weather Service, but there could be tens or hundreds of miles between the next gauge. And their threshold is different because they have a low-lying area and a back bay, and their streets are important to them. These streets, not necessarily the larger scale. Terminology and messaging, all of these things are important that were future stakeholder needs. Did the research, put out a product, engage them. This is what they wanted a little bit more of. Okay, so that's great. But a lot of the scientists, we're like, okay, that's all great, but we're not doing a great job at actually predicting the water level. Right from the science end, there's so many different things we could improve statistically, models, et cetera. So if we look at this is the one equation I have in this talk. Will it flood? It's the and this is like eta, so it's out of like a variable we typically use for water levels. Is the water level, the still water level, greater than that threshold? Yes or no? And it's based on that trend and mean sea level plus the astronomical tides plus the residual. Okay. But there's lots of research that if you have a linear trend versus a quadratic trend, let's say, all of a sudden now because it's data driven, your answer is different, your probabilities are different. What if you did your harmonic analysis to pick out your different cycles of your tides? Right now, we use a standard 37 different cycles. It goes everywhere from like we don't go 3 hours. We have some overtides, kind of like that M2, the main 12.5-hour cycle, and some multiples of that. You go to the spring tides. We have a couple that go a little bit longer, into like the 4.4 year and 18.6 year. We have some of the longer ones, but there's a whole science that goes into how you predict these. And if you change the way you do this, there might be some resonance between your back bays and a certain kinds of forcing. So now you have some more cycles you're not capturing. It might seem down in the weeds, but guess what? You change these. You go from 37 harmonics to 67 harmonics, because that's what the code does by default. All of a sudden, your probability of flooding is different. So these are research projects. Both of these are things we're doing in-house in co-ops. But if you look at that, just that residual part, that probability distribution, you could break that down into a seasonal cycle, your monthly anomaly, which is what you would do your persistence, and then how that hourly anomaly works as well. And now this gets down more into the sun. Over here on the left-hand side, what about instead of that persistence, you don't use a data-driven persistence, you look at climate models. The European Center, they have a climate model that goes out weeks for sea surface height. Can we bring that in? How do you do it? There's actually a dozen models out there. There's a whole host of models. There's ensembles you need to bring in. You take the average of the ensemble, what do? Do you downscale? Because a lot of the ocean ensembles are kilometers wide. I need to know if it's flooding at that location. If it's going to flood, develop probability distributions there. He did some work, John Albers, on CLIVAR. I think Kelsey knows John Albers. He led a project. The European model does great. Better than our data-driven models, especially, maybe not at week 1, because data-driven carries that momentum. But once you get out to week 2, week 3, it does a better job. So it's like, okay, we have these climate models now we can start bringing in, add to our data-driven model. What about this probability distribution? We just used the gamma distribution, not gamma, we used the Gaussian distribution. With an error 1 process, it was like a 1 month lag, or 1 hour lag in this case. But it doesn't really fit normal distributions. So we have a paper that just got released looking at stochastically generated skew distribution. So it's a more complicated noise parameter or set of parameters, and it fits the data distribution much better. And if you do that, we realize that we were underestimating the extreme levels a lot. So we want to bring this distribution into our model. We want to bring the climate model forecast of ensembles into our data-driven model. This will help us as scientists improve the prediction of sea levels. But actually, the first thing we had to do was we had to rewrite the code, because the code wasn't set up to bring in climate prediction. The code wasn't set up to change this. So that was kind of the first thing we had to do. We had to divide it up. And I wasn't part of this, which is great. I'm not an expert coder. I could do like a little bit of coding in like 8 languages, but they need people who can do a lot of expert coding in 1 language. And that's what we did. Unfortunately, we got people that can do that. So this is kind of getting back to that research to help this product. Now, if they hit that first user need, they want to know between the gauges. So a side project going on, because apparently that was a question that lots of people had. They want to know between the gauges. We have this model called CORA, Coastal Ocean Reanalysis. We had a lot of discussion on coming up with a name, and that was fun. Like CORA 1, right? Coastal Ocean Reanalysis. You get down to 500 meters throughout the whole coast every hour for the past 44 years of water levels. And it's a reanalysis. So it might be modeling using AdCirc and SWAN, but then we kind of fit it, developing these correction surfaces on a daily basis throughout the past, again, 44 years. Great product, gonna enhance our scientific understanding throughout. It's a reanalysis, so we force it with ERA5. We have large scale tidal harmonics, we bring it in, and then, like I said, we have these correction surfaces, actually at 2 different timescales. Great product. And actually, not long ago, a colleague of mine, Anna Keeney, and we did a seminar presentation at University of Maryland, their Department of Atmospheric Sciences. And the whole presentation was just on CORA, on both the stakeholder engagement part and also the modeling and the model assessment part. So there's a lot of work that could be done with CORA. And it helps with loads of projects, particularly the coastal high tide flooding thresholds. It's the threshold itself and also the likelihoods. Because you got a great data set. It's almost like an AI ready data set that people can bring in and then use and develop all kinds of statistical models, but also some assessment models. And if you bring it into the product that we have on our website, now you have all these points up and down the coast everywhere. But how do you get this on the web now? Same kind of question as before. Do you look at each one of these nodes, these model nodes, as a gauge? So if a user clicks on it, now you got a whole calendar, and they click on the next point, now you got a new calendar. How does all that work? Right? Lots of questions, but it does give us, in our assessment so far, we get different probabilities of high tide flooding at a more finer scale than we do, than just the tide gauges. Here's an example of Charleston, South Carolina, for different dates. This is October, I think, 2020. But you can kind of see here, as it goes up into the bay, the likelihood of water levels, the likelihood of flooding, you can see through the changes in colors. Not that it changes day to day, but if you pick one day, you have kind of yellow and green probability colors on here, which kind of says you have different levels of probabilities. And there's only one tide gauge. So if you just use that tide gauge like we have in our current product, where you bring this CORA model in, and now we can have, again, spatial variability. We know there's higher probability up the bay than the lower bay for certain kinds of weather events. And depending if it's a tropical storm out in the ocean, it might be higher probability than the outside in the open coast. CORA will help us do that kind of. So this is how we bring in that user need. They need to know between the gauges on a product we already have. We did a lot of research. Now we got to bring it back into the product again. And these are discussions we're having right now. Also, this CORA model skill assessment. How do we even know CORA is a good model to do? We've had lots of comparisons at tide gauges. But what about in that back bay? What about here? What about there? We have some projects with low-cost sensors in place throughout a lot of parts of the country, mainly actually the Southeast and the upper West Coast right now, to do kind of some comparisons. Okay, so to bring it back home now, this is the end here. I mentioned before that kind of that geographic perspective has helped me. So this is a question that my wife asked me that she was asked a lot as a geography student. One of her old professors, April Vaness. I think Peter actually asked a lot of that too.
Sure.
Where's the geography and all that? Okay. the community needs and engagement, where I'm going out, what different physical processes are affecting coastal flooding and the impacts on the other parts of the social and physical environment. What about the communication methods? What about the modeling part or statistical trends or the storms? Right, even just a GIS, geospatial analysis. How do I do downscaling? All of these are questions. All of these have this perspective, that the geographic perspective that can go into this. It doesn't matter if I'm on the modeling side, the data side, the GIS side, the user engagement. All of it can use or make use of that geographic perspective. So I'd say geography isn't all of this. Really. And it's kind of neat. And I mentioned before that, you know, I didn't quite plan a lot of this. Now I'm here, I'm the climatologist within Oceanographers. Before I was kind of meteorology and climatology, coastal science, and a geological survey. I was a scientist before doing census and website data. So I was always kind of, you know, out of sync. But all of this kind of work, right? Even if I didn't predict where I was going to be and what I was going to do, and I have no idea what's going on into the future, but all of this kind of work can again use that geographic perspective and that knowledge of where these numbers are coming from, who is impacting it, who I'm talking to, how is it being reached and used. So that's kind of the idea where the geography is in it. I think these are really important projects. And really, so I want to say thank you for your time in both parts of this topic. Thank you. Are there any questions?
I think there's one online. Can you get to it? The chat.
Yeah. Thank you, thank you, thank you. Can you see slide?
It looks like Gabriella's raised us.
Oh, okay.
You can unmute and talk.
Okay, you can unmute and talk,
Yes,
Gabriella.
yes, hi, this is Gabriela Mundaca. Hi, thank you for your work. And I have two questions. One is a practical question and that's a little bit technical. So I guess I don't know if you have missed you have not discussed accessibility to this data. Is say, for example, how accessible is for homeowners, for insurance companies, for real estate, for farmers, and even for social scientists. For example, I would have liked to have this data to see how this affects the economic conditions of people living on the area which is flooded. So that's the practical question. The second, the other one is somewhat a little more technical. It's about your autoregressive modeling. And I don't know if you have considered because you have this high frequency data and also it's very volatile, this heterogeneity in the series, in the time series that you have. Because, you know, the variance may not need to be constant, right, over time. So I don't know, you have been thinking,
Okay,
what about it?
I can go ahead and make a couple of comments on it. The accessibility is a great question. Right now, we have, you know, a lot of point and click. You have to have a website, you have to look at it, and you have to click on it. We're working with the Weather Service to get some of this information out through their communication methods. And as they reach different communities and their different methods, they can bring our likelihoods of flooding into that. We have developed, you know, like one page flyers. We've been talking about social media posts. Technical aspects, we're making our data available through APIs. That wouldn't be for the homeowner, but that would be for the secondary groups. In Delaware, it could be like the Rascal Group or different local groups that have the technical expertise that can translate the API and the responses into more user-friendly environments. So from a federal point of view, we're trying to make it available for other people, kind of boundary organizations, you would say, or a smaller group, or not necessarily smaller groups, but other groups to translate that. And you make a great point about the periodicity of the data itself. That's something we are working on, especially at the subseasonal, seasonal timescale. That's one of the next things. I mentioned the tidal periodicities and the harmonics, and I mentioned different long-term trends. But we don't really have anything that has the you know, what about if we have ENSO going on right now for the next 3 months? We have that for the longer term annual products, but we don't have it for the subseasonal products. We're not even sure how much that would help. Because you can't get predictions of NAO. We know NAO is a large part of flooding in the East Coast. But you're gonna predict what NAO is over the next 2 months? There is some persistence, but is that gonna be better than your current persistence you have now? So these are questions that we are working on. We're working on with the NOAA research labs, and within co-ops. We are aware of it and we're working on it.
I'm sorry, can I ask you very shortly? Do you experience that, say, the real estate or insurance companies come to you, I mean, not to you, but to your group or to your department and say, well, you know what, we are now trying to put a price for the insurance, the premium, or the real estate, we're gonna sell houses. How is your forecasting for flooding or et cetera, in order to put a price, you know, to housing, to the insurance rates, premium?
Yeah.
That's
No,
very.
Okay, not necessarily for those particular purposes. They are. Now, people have reached out and asked those questions. Yes, we actually had a whole set of presentations we gave to the reinsurance industry and how they could use our high tide flooding and our core modeling for their use. We don't necessarily change, or they are part of the users, right? There's lots of stakeholders and lots of uses. So yeah, their interests and their needs are part of ours, but we don't necessarily answer those kind of questions and asking them how to set prices. You know, we're kind of more focused on engagement, on the predictability of the science part, and we'll help them interpret that, but not necessarily taking that second step in the application. Any other?
So I know we worked together for a long time.
Yeah.
You worked on products or things like this at different scales for many, many years. And so kind of curious, the research and operations, which do you consider the more difficult problem to address? Like which one is a bigger issue for you to deal with?
Okay. I think most difficult is neither. I think it's more that, and maybe it's more towards the operations part, but it's the communication. It's the assessment. Is your product really working? Are people using that product in the way that it was intended? And can they take action based on the information you gave them? Are they changing their plans, or the state of Delaware changing how they create beach nourishment projects? Or are they gonna be having, you know, staffing people for 911 potential flooding or for DelDOT, right? That is very difficult. You can make a product, get into operations. I mean, it's not easy, but you can do that and still not know how well it's working. You can do your research, and research really hard because you're not sure what works and what doesn't work. So you try different things in your research and you fit one data to another data set and you use statistics to compare that. There's a dozen metrics that you can use to say how well things fit. And it looks great. You get a R squared of 0.99, MAEs of 0.001. Great, hey, it gets published, right? But is it usable? Is it informative to people? Knowing if it is, to me, is an extremely difficult question. And fortunately, there are, you know, you can do your research and you're supposed to. You're supposed to gather the minds and figure out your research and do papers or reports or tests or presentations, and you talk about it and discuss it. And then as a group, and I find this really important in the stuff I've done now. You have different people with different experiences and different, you know, agencies, and we have interagency discussions, and the stakeholders. You figure out what part of all this research is really cost benefit to put in that time and will be most useful. Then you figure out how to make that operational. Then you have to get that assessment back. And I think that's the hard part. The research you can do, and a lot of us scientists, we kind of really enjoy that. It's great. But then once you start saying, hey, maybe our prediction, maybe it's not that 5% threshold and say yes or no. Maybe that's not what people need. And what I know is it above average, below average, or average. Maybe they can make an assessment. Maybe they don't need to know 6 months out, but they need to know 2 months out. So it's really Like that part, once you start asking about scientists or. Yeah, I'm not sure, I think so. I think people, so it's that part I think is the most difficult. Yeah. Awesome.
So when we think about the S2S timescale, sometimes for, I would imagine maybe for something like coastal flooding events, maybe there's not enough data even available to understand like the large scale signals from NSO or NAO, because maybe there isn't, like, the observational record might be too short. And you talked about spheres being used to understand maybe the interannular variability and things like that. I mean, what do you see as being like the state of the science in terms of our understanding of things like NSO and NAO? And is it more of a signal than just the long-term climate change signal, which might be actually just more meaningful in a prediction standpoint?
Yeah. Yeah, a few things. You're right, we don't have enough data. We do not. And for coastal flooding, we absolutely do not. Again, like I mentioned, it's at a type of local. You go up and down the coast, you go slightly inland, up basin. Right, we don't have, most of these areas are not monitored at all. Even areas that flood all the time, we don't monitor, and Kevin knows this. Right, and even sometimes it's not even worth putting a sensor in there, because hey, we just know it floods every day. It's not even worth it. But from a scientist and data point of view, we kind of need the numbers to tease out what's going on. And we also, not only do we not have the spatial coverage, we don't have the temporal coverage. In some of the more recent extreme value analysis kinds of assessments, and I think the National Academies put this out for precipitation. Observations alone are not sufficient to come up with sufficient assessment of the probabilities of rare events. Rare events, by definition, extremes don't happen enough. So you start doing these regional frequency analysis kinds of things, and you bring in observations in your surrounding areas, and you extend your time period by sacrificing locality. You can do that, but you also need modeling. And they stated this for precipitation, but we see the same in water levels, especially in water levels. The observational record is not long enough. Yeah. But even if you did, even if you had great spatial coverage and you had long periods of record, it is still extremely difficult. This is kind of where the state of science is to get what is the signal of that subseasonal timescale. You know, I'm not sure if we see an MJO signal. You might down in the, you know, the lower latitudes or Pacific Islands, right? Do we see it up here? Right? We see a strong ENSO signal, absolutely. The Mid-Atlantic, ENSO is the one source of subseasonal predictability we see over here. Not because of those, ocean current waves and those Kelvin waves, but it's really the changing in the jet stream and the shifting, and you have more changing the direction of winds and its interaction on the NAO and some other parts in the North Atlantic that changes storm patterns and some ocean patterns. That's the source of predictability. Even that is really hard. I showed a slide up here early on. What are all the pieces of coastal flooding? You know, what if your soils are saturated and so water levels are high, and when it rains, you start getting coastal flooding? That's not really an ocean pattern, it's an atmospheric pattern. It may or may not be related to some coastal signal. It is really hard to tease it out because you have so many factors. Underneath the Delaware Bay, you have scouring. Scouring happens in the middle of Delaware Bay. If you have excess scouring, you have changing in kind of the small eddies, and you have changing on ocean and on flooding on both sides of the bay, which actually changes because of your bathymetry. You have certain storms that come in, and if it's not, there's a remote wind forcing and a local wind forcing, and they happen at 90 degrees of each other, and it forces water into certain bays. Well, if that's a little bit different, and for an inland bay, you have a small inlet, and Delaware is actually pretty large. But that changes. So long story short, there's too late for that. But there are so many different factors that go into it. It's very hard to tease it out. And this is where I think AI and machine learning come in as well as physical modeling to try to help tease out that subseasonal signal. And I hope we can do it, but I don't know. We remove it for long-term trends. Hey, multiple regression, take out PDO, take out NAO, take out that stuff, take out NCL, great. You have long-term trend. But actually looking at a little bit more refined influence of these subseasonal timescales, yeah, that's what we're working on now. Any other questions?
Comments?
I have a comment to make. John undersells himself in terms of his early days, in terms of everything that you've done with IT and DGS. I think some of those extra things that we do as students and things, that's what built John's skill set. And he underestimates all of that, because I think that's what has given you the skill set that you have today. And I think about the data mill and some of the stuff that you had years ago, and it's really, when that went away, it was devastating to us, but it really set the bar for what we expect in Delaware from having data. And kind of just what we expect in the classroom, what it gave everyone around Delaware in terms of accessibility to data. And so you undersell yourself there, you're being humble about all those things.
Thank you.
But I think, you know, some of the extra things that we build into it, we think are kind of extra things that, you know, that we've done, really kind of build everything kind of in our package of our education and things. So thanks for sharing all that, because I think that's really neat to hear your story and where you've been and where you are today. Any other questions? Otherwise, I think we kind of do have to watch our time, but let's thank John for a wonderful presentation. Really.
Thank you all.